All right. So now we're going to talk about the confidence interval for the difference between two proportions. So the general equation looks, like what we expect. We've got P1 minus P2, right? They're focused on the difference between them. So, excuse me, P1 hat minus P2 hat plus or minus Z alpha over 2. Remember, when we're doing a confidence interval, we're interested to the left and right, so less than and greater. So that's why we always have alpha over 2, T over T alpha over 2. That's where that's coming from. And then our standard error in this case is a bit more complicated, but it's the square root of P1 hat, Q1 hat. Remember, Q1 hat being 1 minus P1 hat divided by N1 plus P2 hat times Q2 hat divided by N2, so the sample size of the second sample, and the square root of all that good stuff. So let's go to the surgeon and general practitioner problem and calculate a 99% confidence interval for that. So let's remember that our P1 in that case was 0.15, and our P2, P1 hat was 0.15, P2 hat was 0.21. If we do that difference, we get negative 0.06. That's a little bit hard to read, so I'm just going to make that a little bit more, a little bit more obvious. There you go. Okay. And then if we do our Z alpha over 2, so for alpha is 0.01, that's 2.58. Again, if you that's on the chapter 8 hypothesis testing, right? If this is the equivalent for two-tail, right? Because with two-tail, you always have to divide alpha over 2, or you could just calculate that by doing 1 minus 0.01 over 2, and that will give you, 0.995. You go look that up, and you'll get 2.58. So now we're going to calculate our standard error. So the square root of P1 hat, Q1 hat over N1 plus P2 hat, Q2 hat over N2. And we get 0.15 times 1 minus that, which is 0.85 divided by 200. And then our P2 is 0.21. So then Q2, P2 hat is 0.21. Q2 hat is going to be 1 minus that, so 0.79 over 200. If we do that whole square root, we get a nice 0.038. So we're going to have negative 0.06 minus our Z alpha over 2 times our standard error, so 2.58 times 0.038, and then our that's going to be our lower margin, our lower edge of the confidence interval. Our upper edge is going to be negative 0.06 plus Z alpha over 2, 2.58 times our standard error, 0.038. And we get negative 0.158 up to 0.038. Now, in much the same way as we talked about earlier today, if 0 is in the confidence interval, then we can't reject the null hypothesis, right? Because we're saying that we think that the difference between P1 hat and P2 hat, or excuse me, P1 and P2 is 0. So if that ends up in here, then we're saying like, it's possible that it's in here. In fact, so we can't reject it. So because 0 is in the confidence interval, we don't reject the null hypothesis. And in fact, if we go back up here, that is what we expected, right? We didn't reject it. This is the surgeons and general practitioners. We didn't reject it on a Z test and a P test, and now we're not rejecting it on a confidence interval test. So this is how you would do that. Let's do one in Excel real quick. So we're going to have a random sample of 200 men, 130 of which said they use seatbelts. We've got 275 women, 175 of which said they use seatbelts. We want to construct a 99% confidence interval of the true difference in proportions. So let's swing on over to Excel here. We have all of our information, right? So X, N, and then P hat, I calculated by, right, this is 130 over 200, and this is 175 over 275. Our P hat difference, right, our P1 minus P2, actually I'm going to write that like this, P1 hat minus P2 hat, yep. And again, we go here and it's 0.65 minus 0.636364. So if we want 99% confidence, that's an alpha of 0.01. So we can go and find our Z alpha over 2, and we get 2.575, which, earlier we got 2.58. That's rounding, right? So these are the same basic answers. This is just the more exact version. And I found that by doing norm.sinv, and I did 1 minus alpha, right? 1 minus alpha over 2. So we can see right here, I did 1 minus J19 is this alpha. So 1 minus alpha over 2, plug that into the norm.s.inv, norm.s being the standard normal distribution. And it spits out our roughly 2.58, which is what we expect. So let's calculate our standard error. This is a bit complicated, right? But we've got our A21 is P hat, P1 hat, and then our 1 minus A21, that's Q1 hat, right? Divided by A20 is our N1, plus our C21 is this P2 hat, times 1 minus that, so that's our Q2 hat, divided by C20, which is this N2, and all of this is under the square root, right? All this is under these, you can see where it's blinking right here. This is one edge of the parentheses, and then, this is the other edge of the parentheses. So it's all under the square root. When you do that, you get 0.044, all that good stuff. So to calculate the margin of error, this is our Z alpha over 2 times our standard error, which is exactly what we did. We just did C24, which is the Z alpha over 2 times A24, which is the standard error. So now to calculate these, we're going to take our P hat difference, right? P1 hat minus P2 hat, and we're going to just subtract the MOE, and you get negative 0.1, and then you're going to take this 0.13636, our E19, and we're going to add the MOE, and you get 0.128 roughly. Now again, 0 is in this, right? So remember, our null hypothesis is that P1 minus P2 is equal to 0. So we cannot reject the null hypothesis in this case, same as the earlier case. So this is how we could use a confidence interval to test, to do our hypothesis testing. Okay, I hope this makes sense. If anybody has any questions, please don't hesitate to reach out. So last thing, let me do a quick example of what I was talking about with the t distribution stuff. So let's say that I want to do equals t dot, let's see, dist rt, and it's going to give me, so now, right, so this is how I have a right tail test, and I'm using a t distribution, and I want to find a I want to find the p-value associated with some test statistic that I just calculated. So I calculated a 2.3, and let's say I have a degrees of freedom of 8. I'm just making these numbers up, and you get that. There you go. That looks nice. However, what happens if I ended up getting a negative 2.3, right? If P1 or P hat 1 is like way less than P hat 2, then sure, I could totally get that. So this is perfectly reasonable. So t dot dist dot rt, and I'm going to have a negative 2.3 with 8 degrees of freedom, and